For more than 50 years, we've lived with an unspoken assumption. It's basically the bedrock for every piece of modern tech you touch.
Right.
And that assumption was beautifully simple.
Mm-hmm.
Next year's chips would automatically be faster.
Cheaper, denser.
Exactly. Denser than this year's. It was a given.
It really was. It was sort of the invisible gravity of the digital age. I mean, that's the guarantee that underwrote the rise of smartphones, the cloud, even the economics that made AI possible.
That guaranteed exponential progress.
Oh.
That was Moore's law. But today, the story has, well, it's fundamentally changed. The progress we all just took for granted is slowing down dramatically.
Yeah.
We are now, in real time, watching one of the foundational trends of our lifetime run smack into its physical and economic limits.
The conversation in the industry has moved past debating if it's ending. I mean, that's done. The entire focus now is on what replaces it, what replaces that automatic exponential progress that powered half a century of innovation.
Exactly. So for this deep dive, our mission is clear. We're exploring not just why this law is failing, but what the world's most advanced engineers are building to replace it. We'll focus on smarter design, the new economics, and how this is all, reshaping global power. So let's start with a bit of clarity. When people hear Moore's law, they think it's like the speed of light or something.
A law of physics.
Yeah, but it was never really that, was it?
Not at all. It was an observation. It started as an observation that then kind of turned into a competitive declaration. In 1965, Gordon Moore just noticed that the number of components transistors on a chip seemed to double roughly every 18 to 24 months.
And once he said it out loud, the entire industry, Intel, AMD, everyone just adopted it as a benchmark. It became a target they had to hit.
A self-fulfilling prophecy, precisely. And the impact was phenomenal. That relentless drive meant the cost of computing just plummeted year after year.
And software developers got a free ride.
They got a total free ride. They didn't have to rewrite their code to be more efficient. The hardware just took care of it. Every 2 years, your phone got better, your computer got faster. But the thing is, exponential trends, by their very nature, they don't last forever. They can't. And we are now hitting those inescapable physical walls.
Okay, so let's unpack those walls. Why is this decades-long trend finally running out of road? Our sources point to three really distinct, unavoidable barriers.
Yeah, the three walls.
What's that first most fundamental wall we hit when we try to shrink a transistor even further?
That would be the physics wall. And the problem is simple to state, but profound in its implication. We've shrunk transistors down to the atomic scale. The gates controlling the flow of electrons are now just a few atoms wide.
That's a scale that's almost impossible to really wrap your head around. If you're building a functioning switch that small, you have to be fighting the basic rules of the universe.
You really are. At that nanometer scale, the classical physics that governs our world, it just breaks down. Quantum mechanics takes over. And electrons stop behaving like predictable little balls following a path. They start acting like waves. And this leads to all sorts of quantum weirdness, but most notably something called electron tunneling.
Okay, so tell us what tunneling means in, practical terms for a chip.
It means the electron can literally just jump or tunnel through the tiny little barrier that's supposed to hold it back. Even when the switch is supposed to be off, it leaks. You get current leakage, you get massive energy inefficiency, and just totally unpredictable behavior. When your switch can't reliably switch, your whole system fails. Or it overheats. We've basically reached the point where we just cannot reliably shrink the switch anymore, period.
So physics stops the shrinkage.
Yeah.
What's the second wall, which I guess is a direct result of this crazy density?
It is. That's the thermal wall. Or you could call it the power wall. When you pack billions, and soon to be trillions, of these switches into a space the size of your thumbnail.
All that activity generates heat.
An immense amount of heat. The power density becomes just unmanageable.
We've actually seen the symptoms of this for years, right? I mean, my CPU today isn't running at 20 gigahertz. Clock speeds stalled out a long time ago.
Exactly. They plateaued because pushing them any higher would literally generate enough heat to melt the silicon. We also saw the end of something called Dennard scaling. That was the idea that as transistors got smaller, their power density stayed constant.
And when did that end?
That ended, back in the mid-2000s, roughly. Once that was gone, power consumption and cooling became the #1 engineering problem. The focus shifted from pure speed to efficiency to parallelism. Now when you build a data center, you spend as much on getting rid of the heat as you do on the processing itself.
Which completely changes the economics.
Yeah.
And that, I guess, brings us to the third wall. The economic wall.
And this one is arguably the most brutal for the businesses trying to stay on the cutting edge.
How so?
It's just a profound shift. The capital required to build a factory, a fab, has gone parabolic. A state-of-the-art fabrication plant now costs upwards of $20 billion.
20 billion. And the tools inside those fabs are engineering marvels themselves. I'm thinking of those EUV lithography machines.
Extreme ultraviolet.
Right.
And those machines, which mostly come from just one Dutch company, ASML, are astronomically complex and expensive. But here's the real kicker. While the cost of making the chips has soared, the performance gain you get from shrinking the transistor is getting smaller and smaller.
Diminishing returns.
Exactly. The cost per transistor improvement, which was the metric that justified all the spending for decades, is failing. It just doesn't make economic sense to sink billions into these tiny high-risk gains anymore.
The margin for easy improvement is gone. So what does this actually mean for you, the person buying a new computer or using the cloud? If we can't expect those automatic speed-ups anymore, where are the gains coming from?
Well, progress doesn't stop. It just changes character. It goes from being automatic in general to being deliberate and specialized. The days where you could just wait for the next chip and get a massive single-core speed bump, those are over. Single-core performance is now almost flat year over year.
So the free ride for engineers is officially over.
It's totally over. If the hardware can't just magically solve the problem, the responsibility shifts.
Right.
Gains are now intensely engineered. They come from massive parallelism, clever new architectures, and this is crucial, relentless software optimization. Performance has to be designed from the ground up for a specific task, and that means developers have to work much, much harder to squeeze out every last drop of performance.
And this is where it gets really interesting, I think, because we've hit these three massive walls: physics, heat, money. The industry's had to pivot brilliantly. Let's detail the new strategies that are replacing just shrinking things.
Okay. The primary strategy, the one you see everywhere, is the move towards specialized hardware, or accelerators. It attacks the efficiency problem head-on.
So instead of a Swiss Army knife CPU that does everything sort of okay,
But inefficiently.
right, we're building custom tools for custom jobs.
Exactly. A general-purpose CPU is just staggeringly inefficient for tasks like AI or video processing. So the industry has designed what are called domain-specific chips, GPUs, TPUs, ASICs, that are built just for specific math operations. A modern TPU from Google, for instance, can run AI workloads orders of magnitude more efficiently than a traditional CPU could ever hope to.
So this isn't about raw speed, it's about efficiency for a given task. If you can't make the transistor cheaper, you make the task 10 times more efficient on that same transistor.
Precisely, which takes us to the second major strategy, which is all about tackling that economic wall. That's modular design and chiplets.
But wait, for decades, the whole idea was to make one big monolithic chip, a single flawless piece of silicon. Wasn't modularity a bad thing?
It was, historically, because connecting different pieces of silicon was slow and complex. But the economics have forced their hand. As chips get bigger, the probability of having one tiny fatal defect somewhere on that huge piece of silicon just skyrockets.
So your yield, the number of good chips you get per wafer, just plummets.
It plummets, and the cost per good chip explodes.
So the chiplet solution is what?
You break the design up. You divide it into smaller, specialized modular tiles. You'll have a compute tile, an I/O tile, a memory tile. These smaller pieces are much easier to manufacture with high yield. Then you just integrate them into a single package. AMD has been a master of this, mixing and matching different modules to create these incredibly powerful yet cost-effective processors.
Which means the whole focus of engineering has shifted. It's not just about mastering the silicon wafer anymore, it's about mastering the packaging innovation, how you connect all those little pieces.
Absolutely. The connections between the chiplets have to be insanely fast and efficient. And speaking of density, that leads us right to our third big solution, 3D stacking. Vertical integration.
If you can't build out anymore, you have to build up.
It's the only way to increase transistor density without fighting that physics wall again. By stacking dies right on top of each other, say logic on top of memory, you dramatically reduce the distance that data has to travel.
And that helps with the heat problem, the thermal wall.
Directly. Shorter travel distance means lower latency, and less power is used to move data, which means less waste heat.
We're basically building tiny little high-rise cities for data inside our computers.
That's a perfect analogy. But that complexity means you can't design hardware and software in separate silos anymore, which brings us to software-hardware co-design.
So you're not just writing code for a general chip, you're designing the algorithm and the physical architecture at the same time.
Correct. You build the hardware to specifically run the most efficient algorithms, and you write the algorithms to take advantage of the hardware's unique layout. You get these hyper-optimized systems that are just far more efficient.
Okay, and finally, what about materials? Are we stuck with silicon forever?
No, not at all. The materials science frontier is huge. We're looking at things like gallium nitride or GaN and graphene. GaN is already showing up in high-efficiency power adapters, but the really radical shift is changing how data moves inside the chip itself.
You're talking about using light instead of electrons.
Exactly. Photonic computing. Replacing the movement of electrons with photons with light inside and between chips. Light is faster and it generates far, far less heat than an electrical current. Using light for data communication is probably the key to unlocking the full potential of all these other ideas like chiplets and 3D stacking.
Now, let's zoom out a bit, because this isn't just a technical challenge. The end of this easy scaling changes, well, it changes the global rules. What are the broader economic and geopolitical ripple effects here?
It completely rewrites the economic playbook because the cost of building these fabs is so astronomical and the tools are so complex. Manufacturing power has become extremely concentrated. It basically sits with a handful of companies and a handful of nations. Taiwan, South Korea, the US, and the Netherlands.
TSMC in Taiwan is probably the single most important company in the world right now.
Arguably, yes. The physical control over the most advanced factories is now paramount. The competitive advantage isn't just inventing a better transistor anymore. It's about system-level design, software, and most importantly, supply chain resilience. Guaranteed access to manufacturing.
Which has triggered this massive global response. We're seeing governments suddenly care a lot about strategic independence.
Correct. The pandemic really exposed how fragile the supply chains were. So now governments are pouring hundreds of billions into subsidies, things like the U.S. GPS Act, similar efforts in Europe to onshore manufacturing capacity. They know that if innovation is harder and slower, having your own sovereign control over that core production is non-negotiable for national security.
So, to bring this all home, if Moore's Law is really over, the future won't be about that guaranteed automatic growth that just lifted all boats. It's going to be about better ideas, smarter trade-offs, and just ingenious system-level engineering. Progress now demands creativity, not just pure shrinkage.
And for you listening, this translates into real-world changes. Device improvements will feel different. They'll be more specialized. You'll see dramatically better battery life from specialized power chips or incredible AI features running right on your device because of a special accelerator. It won't just be about the raw clock speed number on the box. Optimization is now the name of the game for everyone, from the hardware designers to the people writing your apps.
We've established that the innovation mode is shifting from transistor mastery to system-level design and specialization. This forces us to redefine what progress even means. In a world without automatic exponential progress, where complex systems like chiplets and 3D stacking rule, what specific computing capability, whether it's ultra-low power AI inference at the edge, rapid optical data transfer between chiplets, or perhaps perfected gain power management, do you think will become the single most valuable technological bottleneck in the next 5 years? Something to keep in mind as the computing industry embraces this new, slower, but decidedly more creative era.